this video, we're talking about part 1 of the fundamental theorem of calculus. And remember that the fundamental theorem of calculus is a theorem that relates the derivative to the integral. And the reason that it's called the fundamental theorem of calculus is because it's very important, because the first half of calculus is all about the derivative, the second half is all about the integral. Those are the two major concepts from calculus, and so the theorem that relates the two, that defines the derivative in terms of the integral and the integral in terms of the derivative, is sort of that hinge point. It's that linchpin of calculus that relates the two areas together. So what we're going to be doing in this video is talking about how to find the derivative of a function using an integral, essentially. So we've been given this equation here. We've been told that we have some function f of x, and it's equal to this integral. And what we need to do is find the derivative of f of x, and of course the derivative of f of x is f prime of x. So oftentimes the easiest way for people to do this is to use a chart that tells you exactly what you're supposed to do in a particular situation. This part 1 of the fundamental theorem is going to be all about these limits of integration here, this lower limit of integration, which in our problem is x squared, this upper limit of integration, which in our problem is cosine of x. Depending on the types of values that you have in your limits of integration, whether you have a constant, whether you have just a single variable x, or whether you have some function like we do here, we have a function x squared and a function cosine of x, is going to dictate how you approach this problem. So let's just take a look at that chart for a second. So this is the chart that we have here, and you can see that in the first row we have f of x is equal to the integral from a to x of f of t dt. So the important thing to know there is that that lower limit of integration is a, and that a represents a constant. The upper limit of integration is x, so it's a variable. If you have that particular scenario where the lower limit is a constant and the upper limit is the single variable x, then all you have to do is you take that function f of t that's inside your integral and you just plug x in for t, and that's your answer for the derivative of f of x. If you have the opposite situation, like in this second row here, you have f of x is equal to the integral from x to a. That lower limit of integration is the variable x. The upper limit of integration is a, the constant. When you have that situation, all you want to do is reverse those limits. So you essentially want to turn it into a problem like this one in the first row. You want to switch those limits of integration and multiply by -1, and then you go back to your directive from the first row where you just plug x in for t. Now you can follow the steps in this chart. You can match up the kind of problem you have to this chart. This third row here is lower limit of integration is a constant, upper limit of integration is some function. The fourth row is lower limit is a function, upper limit is a constant. And the fifth row is lower limit is a function and upper limit is a function. And this will tell you how to solve for the derivative of f of x. But I want to talk about why this actually works here. So what we want to do is we want to generalize this equation right here. So if we leave f of x on the left-hand side, we've got f of x here on the left-hand side. And on the right-hand side, we keep the integral here, but we've got two functions for the limits of integration. So instead of the functions themselves, if we call them functions in terms of x, so we'll just call the lower one g of x and the upper one h of x, doesn't matter what they are, but basically they're just functions in terms of x. And then this function here inside of the integral, it's a function in terms of t. So let's pretend that it's r of t and then we have dt. So we just really generalized this problem that we were given. When we take the integral of something, the notation that we like to use, if we're taking the integral of r of t, then the integral of r of t is going to be capital R of t. So we use that notation, and basically we're saying we took the integral and we got capital R of t, and now what we want to do is we want to evaluate this function, capital R of t, over the interval that we were given. So we want to evaluate it over the interval g of x to h of x, and that's what this notation means here. It means evaluate this over the interval g of x to h of x. So when we do that, this is just a definite integral. We always plug in that upper limit of integration first, and we're plugging it in for t. So plugging h of x in for t, we get r of h of x. Then we always subtract whatever we get when we plug in the lower limit of integration, which in our case is g of x. So we subtract, and then we put this g of x in for t, so we subtract capital R of g of x. So now we have f of x, our original function here, f of x, instead of in terms of this integral here, we have this equation. And if we want to then find the derivative of f of x, which is f prime of x, the derivative, then we would say f prime of x, and we can take the derivative of this right-hand side one term at a time. So the derivative of capital R, remember the integral of little r was capital R, which means that the derivative of capital R is little r. So we end up with small r of h of x. Going to this step right here is going to require us to use chain rule, because remember, chain rule tells us that we leave this inside function alone, but then we have to multiply by the derivative of the inside function. So the derivative of capital R of h of x is small r of h of x times h prime of x, the derivative of this inside function h of x. And then same thing here, we end up with minus small r of g of x, but then we multiply by the derivative of the inside function, so we multiply by g prime of x. And this is really the important formula that we would need to remember, and we could always derive it again if we wanted to. But if we use this formula every time, then we can recreate that chart that we were looking at the beginning. So if we want to find the derivative of this original function using this formula here, let's go ahead and try it. So f prime of x, the derivative, which is what we need to find, is going to be equal to, we have little r of h of x. Well, we know that little r is t squared plus 2. So we need to plug h of x into t squared plus 2. Well, h of x is our upper limit of integration. So we need to plug our upper limit of integration, cosine of x, into t squared plus 2. We need to plug that in for t. So if we take cosine of x and we plug it in for t, we're going to get cosine of x squared and then plus 2. So we end up with this cosine of x squared plus 2. But then going back to our formula, we have to multiply by h prime of x. Well, that's the derivative of h of x. H of x is cosine of x, and the derivative of cosine of x is negative sine of x. So we end up with here multiplying this by negative sine of x, and that takes care of r of h of x times r prime of x. Then, according to our formula, we're going to subtract r of g of x. So we're going to subtract r of g of x. Well, g of x is this lower limit of integration here, and we're taking r of g of x. So r is t squared plus 2. We need to plug our lower limit of integration into this t squared plus 2. So if we plug x squared in for t, what we end up with is x squared and then squared, because we took this x squared, we put it in for t, so we end up with x squared and then squared plus 2. But then we have to multiply that by g prime of x, or the derivative of our lower limit of integration. The derivative of x squared is 2x, so we have to multiply this by 2x. And now we just simplify, so we can say that the derivative f prime of x is going to be equal to, applying this squared exponent here, we get cosine squared of x plus 2 multiplied by negative sine of x. Then here we have this minus sign, we have the 2x, we can bring that out in front, so we'll get minus 2x multiplied by x squared, and then squared again is x to the fourth, so x to the fourth plus 2. Then if we simplify one more time, so f prime of x is going to be, we'll bring this negative sine of x in front, so negative sine of x times cosine squared of x plus 2 minus 2x times x to the fourth plus 2. Now I'll just show you one example of why that works if we go back to our table. So what we're talking about here is we're comparing this table to this formula that we boxed here in red. So if we just look at the first row here in the table, this row right here, what it says is that in order to find the derivative f prime of x, if f of x is equal to the integral from a to x of f of t dt, that if we want to find the derivative f prime of x, all we have to do is plug x in for t. So if we look at our formula here, why does that make sense? Well, the reason is because that lower limit of integration is a, which is a constant. So here, if we compare this to our formula, our lower limit of integration is g of x right here. If g of x is a constant, what happens then to our formula? Well, if we look down here, we see g of x and we see g prime of x. Well, g prime of x, that's the derivative of g of x. The derivative of a constant is always going to be 0. So if g prime of x is 0, then we're going to multiply r of g of x by 0. This whole second term right here is going to net to 0, and you're just going to be left with r of h of x times h prime of x. And of course, if we look at our table and the upper limit of integration is x, in other words, if h of x is equal to x, then the derivative of h of x, h prime of x right here, is the derivative of x. Well, the derivative of x is 1, so this value right here, h prime of x, becomes 1, and multiplying by 1 doesn't have any effect, so this formula reduces to f prime of x is equal to r of h of x, and if we said h of x was equal to x, because the upper limit of integration is x, then we can say that the derivative f prime of x is equal to r of x, since h of x is equal to x. And that's why in this how to solve it column, the answer is just plug x in for t, because all we have to do is take x and plug it in for t into our function here. So we'd plug x in for t, and we would end up with the derivative of f of x is x squared plus 2. And that would be the case if the limits of integration given to us had been a constant for the lower limit of integration and just x for the upper limit of integration. So that's why this table can save you some time, because it tells you exactly what to do when you have certain types of limits of integration. But really, it always comes back to this formula here that we found in the first place. If you always use this formula, you'll always get down to the right answer. And that's how you use the fundamental theorem of calculus to find the derivative of a function in terms of an integral. Could you use some extra help with math? Click the button to head over to calculusexpert.com. It's where I've collected and organized all of my best resources, including exclusive videos, notes, quizzes, and even formula sheets. It's the perfect resource whether you're struggling, or if you want to take your learning further, or even if you just want to save yourself some time studying. So check it out, because I know it'll help.